Testing. And we're back. Great. So, we're back again today. About it all, but today's a new day. So hopefully we'll make some more progress on it today. One can only hope. So last time we stopped here. Where was that exactly? Further down, perhaps? No. Probably somewhere here. Yeah. Step 2, implement. No, np log sum exp. So the numpy log sum exponential. And yeah, the squeeze the reduced axis. There's some meta level knowledge that I'm missing. Like what it means to squeeze the axis, or what that looks like in practice. Because we got an explanation down here about how it looks, or no, not how it looks, but how it works. But it isn't saying much to me. Where was it? Squeeze the reduced axis. Squeeze the reduced axis equals remove the size 1 dimension that was created by a reduction. So on a 2D array, let's say, we have then an x-axis and a y-axis for a height and a width. One of those axes is going to be 1 then. And we're going to remove that completely. When you reduce over an axis, for example max, sum, or your log sum exp, you can keep that axis as length -1. With keep dims true. So if we have this parameter here, then we keep it as length -1. Or we can drop it entirely by using keep dims false. Okay, so the input shape is NC. So I don't know why you used those letters, but I mean, this has to be the rows and this is the columns. So when we reduce over axis -1, the c-axis or the column, C for column makes sense, I suppose. If we have keep dims equals true, then the shape will be, oh, it says n for like as a placeholder simply, like in math when you use n for a variable number or a variable, whatever. So resulting shape is whatever that could be, and 1 if we keep dimensions. The reduced axis is still there, but the size 1. And if we do keep dims false, then resulting shape will be simply whatever the first dimension is, or the rows in this case. The reduced axis is removed. But I suppose the way I'm explaining it only works on 2-dimensional arrays. I have no idea if we're going to work with 3-dimensional arrays further along. Maybe. Then that would make it even more confusing. And so squeezing means converting this structure, this shape, to this shape by removing that length -1 axis. Why keep it then squeeze later? While computing log softmax. I'm still not entirely sure what log softmax is. Like concretely, is it a function? What does that function do? Or I might have forgotten it simply from yesterday. I'm gonna try and ask. What does log softmax refer to when in relation to large language models or AI or neural networks?
Sure, let's break it down. So in the context of large language models or neural networks, a log softmax is basically a function that takes in raw scores, like the outputs of your neural network, and converts them into log probabilities. Basically, you first apply a softmax, which turns scores into probabilities that sum up to 1, and then you take the log of those probabilities. And why do that? Well, it's useful for certain loss functions, and it makes the math a bit more stable and easier to handle. So in short, it's just a way to represent probabilities in a log scale, which is common in training language models.
So the softmax part is simply to turn all the results into a probability list or whatever, and then squeeze them together so they're simply like combine into one, or like the different parts become the whole probability becomes 100% when split between them, or combined, or whatever. Is that kind of correct?
Yeah, that's pretty much spot on. So the softmax part is really about taking those raw scores and turning them into a set of probabilities that all add up to 1. And then when you take the log of those probabilities, you just get the log softmax. So it's exactly what you said. It's about making everything sum up to a total probability of 1 and then transforming it into a log scale. So yeah, you got the right idea.
So you're turning the probability numbers, like floats or something, into a scale for stability reasons.
Exactly, that's a nice way to put it. You're taking those probability values and putting them onto a log scale. And the reason for doing that is mainly for numerical stability. It just helps the model handle really small probabilities or really large values more smoothly and avoid numerical issues. So yep, you've got it.
Okay. So LSE log sum exp, this function here. We have the logits, the axis equals -1. I don't know if that means like the last axis or whatever. And keep dimensions true. We will get this shape. We simply return that shape. Logit minus LSE broadcasts row-wise without ambiguity. If your function API says keep teams false, you return the squeezed result so callers get n instead of n1. How to squeeze conceptually. Remove the size 1 axis that corresponds to the axis you reduced over. In NumPy terms, this is what np squeeze does. So say there's a function for it as well. Specifying the axis ensures you only drop the one you reduced. Tiny shape example, logit.shape. So 5 and 7. And we reduce over the -1 axis. With keep dimensions true, the result becomes 5, 1. So we reduce this axis to 1. Then when we squeeze that reduced axis, we remove it completely. Then if you're returning from log sum exp, keep them false, you return the, okay. So you don't, okay. Bottom line, the reduced axis is the dimension you aggregated over. Squeezing it just drops that now useless length 1 dimension from the results shape. Okay. I feel like I need to go through this one more time here. So we have the variable x, we set it as a, we convert the x, what do you call it? Parameter, correct. The x parameter to a float array. And then we create the m variable and we get the max values. If this is a 2-dimensional array, then if this is a 2-dimensional array with 3 columns and 2 rows, we will check each row for their corresponding max value. So it has 3 to pick from. So you take the max value, like say 5 and 4 if they're the highest ones. And since we have keep teams here, so if we do true, then we'd return a what exactly? I'm having a hard time picturing the shape of M. Maybe if I simply can I do this? This feels illegal somehow. I've completely forgotten how to start a Python script. Like, how do you even... Oh my. Okay. If name, okay. So I could simply do np log sum down here, but let's do if name main. Then we call np log sum exp. And we also need to pass along can I do simply np array? Wait, 2D array 2D? No. No, it's simply this is a 2D array. So let's say 1, 2, 3, and 4, 5, and 6. And let's say axis -1 to keep that as the default, and set this to true to keep that the dimensions. And then if we run it, np torch basics apply. Okay. No module name numpy. Wait, do I need to be in and then run it here? Okay. I need to be in the correct environment to run it. That makes sense. And so 3 and 6 is the shape of M. And what if we were to simply pass this along as false? Then we can't do the calculations. Just wanna know the number though. Interesting, so we still get the... I guess I could have seen that up here. But we still get the same values, but we don't get the same structure. I suppose np.squeeze is the correct function to call, but just simply squeeze y. I mean, that's what we're returning, but I don't know why we're doing this. It still feels like I'm missing something crucial. Okay, let's go back down to okay, here. So broadcasting, that's nowhere here, is it? I don't think so. Explains broadcasting and Logit. Logit is the model's raw score before you turn it into a probability. So they could be integers like these. But these would be the probabilities approximately instead. Where we keep Logit's not probabilities during training, numerical stability. We use logs of max and fused losses. For example, cross entropy. We haven't even gone over that yet. Convenience. The model naturally outputs linear scores. Converting to probabilities is the last step for evaluation or sampling. Quick invariance to remember. Logit, larger probability. That's easy to remember. I don't know what monotonic means, though. Adding the same constant to all Logits doesn't change softmax probabilities. Adding the same constant to all Logits doesn't change softmax probabilities. Oh, that makes sense. If we add the same amount to all of them and then have reduced them down equally, then nothing has changed fundamentally. For binary, the logit is the log odds. Log odds. Positive logits favor class 1, negative favor class 0. I don't know if 0 said here is for logits or if it stands for values or something. One logit. Okay, so the C is how you say it here, probably. So probability of class 1. What's the difference between class 1 logits and others? Short version, a class 1 logit is just the raw score the model gives to class 1. It isn't special. What matters is how it compares to the other logits. Binary classification, you'll see either one logit or two. Single logit, sigmoid form, one number. It's the log odds of class 1 versus class 0. Two logits, softmax form. Logit C0, C1, only difference matters. You can add the constant to both and nothing changes. So you can think of it as the class 1 logit as relative to class 1. Key idea in binary, a class 1 logit is mod reference. But what does class 1 even refer to? Why class 1 shows up in loss functions? Cross entropy picks the log probability of the true class. What is classes? It hasn't been explained yet. I mean, I know what classes are in like Python, but I'm a bit confused about its purpose here. Great question. Classes just means the set of possible choices your model can pick from on each example. Okay, so all the choices, okay. Plain meaning, if you're sorting emails, classes spam and not spam, 2 choices. If you're tagging sentiment, classes negative, neutral, positive, 3 choices. In our blob toy dataset, classes, left blob, right blob, 2 choices. I have no idea about blob toy dataset. That's probably something that I missed further up. In an LLM next token task, classes equal the entire vocabulary. Every token is a class. If your vocab has 8,000 tokens, that's 8,000 classes. How it shows up in code. You batch and training examples at once. The model outputs logits, raw scores with shape and C, where n equals batch size. Okay. So this is the batch size. And C, number of classes choices. You also have targets, the correct answer with shape N, where each entry is an integer class index in 0 to C1, C minus 1. Examples tiny. Okay, 3 examples. So N3, we have a batch size of 3 and 4 classes. And the shape of the logits in that case would be 3 and 4. Okay. And we have these random values. Or these 4 classes, I suppose. Random classes. Targets equals 0, 3, 1 means example zeros, true class is class 0. This one. This one. Example 1's true class is class 3. We don't have that here. Example 2's true class is class 1. Softmax turns each row of logits into probabilities over the C classes. Each row sums to 1. Cross entropy then looks up the probability of the true class for each row and penalizes low values. So we're basically are we checking like 3 times and then cross entropy somehow checks which ones are the best of those 3 times? Tying to your more map. Exercise 10 toy classifier. Okay, so that's the more whatever it call it toy classifier. 2 blobs simple. Your tokenizer and LLM later. C equals vocab size. Thousands. Each next token is a class. Logits come from hidden dots probabilities and dot values. W vocab plus B to shape and vocab size. Cross entropy uses the true next token ID in targets. Not entirely sure about this last part here. Classes equals options. C equals number of options. So C doesn't stand for columns, it stands for classes. Okay. And Logit is the batch number and the classes. Targets is the log softmax of the logits. Each entry in between 0 and C minus 1. So classes minus 1. Softmax probabilities over classes or cross entropy. How wrong given the true class? If you want, give me an example you care about. And I'll map it out to the target shapes you can see completely. Okay, so vocab size, say 20, target ID 42. Let's see. how it's going to visualize that for me. I had to check something. If vocab size equals 20, then you have C20 classes. Valid class token IDs are okay. Okay, that makes so much sense. I simply thought it would be easier if we had a smaller vocabulary, but I didn't. I didn't picture how that would impact the target ID. Let's still read this. A target ID of 42 is out of range and indicates a mismatch/bug. What this means: shapes Logit's N and 20 targets M with values in 0 and 19. Cross entropy. When it indexes the log probability for true class 42 can't be looked up, there is no column 42. In PyTorch, this raises an error. In NumPy, you could hit an index error too. Why it happens? Common causes. You loaded a tokenizer with a large vocab, for example 50, but your model head is size for 20. You remapped trimmed vocab, but didn't remap data as a targets. Crop the data, were off by 1 bugs. How to fix? Make vocab plus head match. Find linear layout. Validate targets before loss. Masking, okay, in advanced. I ain't even gonna read this. Is mental model classes equals your choices per step. For next token prediction, each token in the vocab is a class. For next token prediction, each token in the vocab is a class. With C equals 20, there is exactly 20 choices. IDs 0 to 19, anything else is invalid. Okay. What if I were to simply do it like this then? ID 18. And it should give me an example or shape. Perfect, let's pin this to something concrete. Vocab size C20, valid class token IDs are 0 to 19. Target ID true class 18 means the correct next token is ID 18. I suppose target ID is something we trained on. Logit's 1 score per token. Shape 20 for a single example. Or 120 if you keep a batch dimension. Okay, shapes you'll use in your NumPy. If your NumPy CE expects C and N, make a batch of 1. So Logit's shape equals this. Targets plus shape equals 1. With targets 0 equals 18. What softmax does here, some mathematical craziness. What cross entropy uses. Cross entropy for this one example is negative log prob of the true class. How this maps to your functions. Mental checklist. Classes equals tokens. Here 20 classes equals 20 logits. Target 18 means pick index 18 from the log softmax row. I'm still not getting it. I'm still confused. Let's go back to the beginning here. So follow these 5 micro steps exactly. You'll write the code, I'll give you recipes and checks. In your Venvet, I did that. I also did this. Maybe it simply didn't like stick in my head. Can I do it like native Rappler? Oh, okay. Create an array. Can I simply do it like no? I don't even know how Rappler even works. I shouldn't simply do like this. And I'm plus 10. No. What if I were to 1, 2, 3 and plus 10? No. Then what's the point? Wait. NP array. Wait. And 1, 2, 3. I don't even know what I'm doing. axis equals 1. Keep dim equals true. No. So this is not working out. It's, okay. I mean, I already did this 2 times. Vector math. Give me more of this to help me get my head around the concepts involved. Maybe I can get some more exercises, like tiny exercises, to learn like the basic functionality, because this isn't working. Okay, so perfect. Let's do hands-on vector math workout. You'll type everything yourself. For each drill I give task what to type. Expectation numbers of or shapes you should see, why it matters, how it ties to softmax CE. LEMS. Use numpy, import numpy as NP. If anything diverges, tell me the step plus what you saw. Scalars and 1D vectors. Task, make A and P, okay. Do A plus 10, okay. And I should expect this. Okay. So A equals NP. Maybe I should do it like oh, not shift enter. Kill. Then what should we call it? A1. Def A1. Oh. And so A equals NP array, numpy array. And 1, 2, 3. Does SID type NP not float 64. And then we do A plus 10. Print A. No, I should. It's much simpler to simply print them. Print A times 2. Print A divided by 2. And print A raised by 2, I think. 1. It should be raised by 2. And then if we were to run it, 11, 12, 13, 2, 4, 6, 0.5, 1, 1.5, 1, 4, 9. And this corresponds perfectly with this. Why element-wise transforms are bread and butter before reductions. Okay, so this is good to know before we do reductions. Okay. I can do a 2. So A equals np dot array one, 2, 3 d type np dot float 64 and a to print is a at a. Okay, let's run this now. Then we still don't get the correct one. Now though, 14, and that's since dot product. The dot product of a dot a, is that how you say it? A dot a, maybe, becomes 1 times 1, 2 times 2, plus 3 times 3. So you multiply itself, each value with itself, and then add them together. And dot is the building block of Logit. Okay. And then we have a 3. So a equals np dot array 1, 2, 3. D type float 64 again. And then we do a equals np, let's call it b equals can simply do print again, why not? Np dot square root of the dot product. So the square root of 14 then. 374165. 374165. Why norms appear in normalization and attention scaling. So we call this an L2 norm. Okay, I don't know why you do a square root for normalization. I don't know what attention scaling is either. I'm still leery about reductions, so let's go through each one of those. Explain reductions. Okay, so reductions equals operations that collapse one or more axes by aggregating values. The sum, the mean or average, the max, etc. They turn an array into a smaller array. For idea y, you often need a single number or a per row per column summary. Loss means over the batch. Okay. Normalization, subtract row mean or row average. Need a per row value. Stability, log sum exp is a reduction used inside log softmax. The API, NumPy versus PyTorch. NumPy. Okay. So this is the difference simply. Shapes, memorize these. Let x dot shape equals batch size and classes. So if we were to do x dot sum or mp dot sum or whatever, and then axis minus 1, then we reduce last axis. Does that mean we simply remove it? That's what's so confusing. It says operations that collapse one or more axes by aggregating values. Do we simply remove the whole, like, the whole classes? That can't be right. Reduce last axis. If we do axis 0, then we reduce the first axis. But if we do axis minus 1 and keep dimensions, then we... okay, so I guess we actually do delete it completely. But if we keep the dimensions, then we set it to 1 as a default. Same numbers as n, but keeps a length minus 1 axis. So it can broadcast back onto NC. But is this like a list or something? I mean, it's called an array, but it can't be... I suppose this is also called an array, but in my mind this is a list. But I suppose calling it a one-dimensional array is more accurate. So this is still an array, but a one-dimensional one. But keeps a length minus 1 axis. Why length minus 1? Just keep dims true when you immediately combine the result back with x. For example, with row-wise subtraction. Common reductions, what they compute. Sum, mean, prod, max, min. Value reductions. Argmax / argmin, index reductions, any / all, logical. Log sum exp, stable. Log sum exp, same signature pattern as sum slash max. Multiple axes. Okay, so for a 3-dimensional array, batch time channels. So C is for channels, not classes. Wait, maybe it's simply in this. The vocabulary is kind of confusing. X.mean equal x. So the average of axis 0, 1 shape C. Mean over batch and time. Sum axis 0, 2. Keep dimensions true. 1, 1. The shape is like that. It's the summary of the time, probably. Why keep dims matter practical? You want row-wise operations like row centering, x minus x mean, x axis equals -1, keep dimensions true. Element-wise operations keep shape. This is the element-wise operations, I think. Reductions collapse axes. Optionally keeping them as size 1 with keep dimensions true. Keep dims when you plan to broadcast back onto the original array. If any part of this is fuzzy, tell me which bullet, for example, multiple axes or argmax versus max, and I'll expand with a tiny example. Well, I'd say like half of it is pretty fuzzy. I suppose if I had studied math in like the recent years, then maybe this wouldn't be as confusing. I suppose in one way you could say that this might be like a bit overkill to understand the math behind it, but it feels important somehow. I guess I could simply copy and paste like the math functions and get it working pretty easily, but I'm gonna try some more before even considering that approach. So let's go to the B. I'm just gonna take a short break. I'll be right back. Alright, I'm back. So, let's keep going. I have this vague hope that if I like work through enough exercises and work with the numbers and the underlying math, then somehow it will simply click at one point. Like everything come together in my head. That might be a vain hope, but it's the only hope I have. It's like, because I'm not opening a math textbook and reading through it. I'm simply not doing it. So, suppose we could do B1 next. And so, row-wise max, keep dimensions. And we call that X. NP array. And here we create a two-dimensional array. And we do 1, 2, 3, and we do 4, 5, 6, and we do d-type float 64 or np dot of course, like that. So the shape becomes 2 and 3. Okay. And I don't know if my calling it to like rows and columns and stuff like that, if that's making it worse. So I'm gonna try and simply ignore calling it like rows or whatever and simply think of the shape. I'm gonna try it anyways. And then we can do m equals x max axis 1 keep dims through. And we can do x dot max instead of doing np dot max and then passing along x. So this is the same as doing this and then x like that. Okay, but x dot max and axis 1. That has to be this axis, doesn't it? Will we get 3 values then? Like 4, 5 and 6? No. Expect 3 and 6. Shape to 1. Oh, because this is one dimension or one axis. I'm still having a hard time to wrap my head around like what this refers to. It refers to an axis, but why is it axis 1? I mean, the 3 and the 6 has to refer to those as they are the max values in each. I don't want to call them rows, but let's call it the first dimension. They are the max values in the first dimension. And the shape becomes to 1. Is that because we have 2 values? Or is it because the values are separated? It has to be because they're separated. Because we're keeping the dimensions. Okay. If we were to do have x the full array and we remove m, then we would remove 3 from all of those and 6 from all of those. I'm not gonna lie, it's a bit confusing, as everything else. Why keep dims? Let's really print here. And we call B1. So this is correct. Why keep dims let 2-1 broadcast against 2-3 row-wise operations? This is exactly what we do in logsum.exp. Why? Keep dims let I suppose it's because we keep the structure. And as we keep the structure, it can like lay against it somehow. I mean, I think I understand like the underlying function, or should I say an underlying logic behind it, but I don't understand the purpose, and that's what keeps tripping me up. Because I can step by step see that, okay, so we remove those 3 from those 3. Okay, and we do the 6 here. That makes sense. But why? Why do we do this? It says Andy 2-1 here, broadcast against 2-3 row-wise operations. This makes sense. This makes sense in another way, since we have 2 dimensions. So the first dimension and the second dimension. and we want to keeping the dimensions makes it certain that we actually remove it from the correct place. Or we remove it from the correct dimension as well, I suppose. Column-wise centering. I'm just gonna move on for now. So x equals np array. I'm just gonna assume that we have the same array here. And D type. Shape 1, 3. No. Wrong line. This is still shape. Shape 2, 2, 3. And then we have C equals x dot mean. Axis 0. Keep dims equals true. Here we can say shape 1, 3. Okay. Then print x minus c. What? Expect rows centered per column. The first column around 2.5. Well, this is minus 1.5 and 1.5. Should I do maybe like this and give result? that result is exactly correct for column-wise centering. Column means first column 1422.5, second Okay, I'm so lost. There's either a fundamental problem with my brain, or with my education, or with this teaching style. Because this means nothing to me. I could somewhat follow this one, but this means nothing. Expect rows centered per column. Okay, so we're back to using rows and column speech. So okay, so maybe that's acceptable. Okay, let's go back to doing that, and then we call so we have 2 rows and 3 columns. So rows centered per column. What does that even mean? Do you mean that we average out? Like take 1 plus 2 plus 3 and divide it by 3? Or is it 1 plus 4? So 5, and then 2 plus 7, or 2 plus 5, 7, 3 plus 6, 9. I feel like I'm entirely missing the point. I don't understand this at all. Like nothing. It makes sense to me. Okay, what column-wise centering means? You have a 2 times 3 table. So 2 rows, 3 columns. Column-wise centering. For each column, subtract that column's mean from every number in that column. So... okay, so it is like that. And collect them as a 1 times 3 row. Subtract those means from the original table column by column. So column 1 subtract 2.5. And 2. Okay. And that's the result, exactly as you saw. Y numpy code looks like x minus c. X is your 2 times 3 table. C is the 1 times 3 row of columns column means 2.5, 3.5, 4.5. When you do x minus c, NumPy conceptually copies that row down to both rows and subtracts per column. It doesn't actually copy, it just acts as it did. That automatic size matching is called broadcasting. Okay, so finally we have a useful explanation for broadcasting. If you print C, you should literally see let's try that. Print C. Okay. And then we do print X. So this one gets removed from that and that, this one removes from that and that, this one from that and that. And this is the result. And that's called broadcasting. Okay. How you can sanity check it. Recompute the column means of the result. They should be 0 for every column. Oh, the mean of... okay. So... like if I were to do... like np dot mean and axis 0 keep ims true. Like that. 0, 0, 0, 0. Okay. Because the average of -1 and -1.5 and positive 1.5 is 0. So that makes sense. Why we practiced this? The why. This is the exact shape pattern you'll see for stable log softmax later. Compute one value per row or per column using a reduction like mean or max. Keep it as a size -1 axis. So the shape is N1. Oh wait, is this not minus? Wait a moment. Do you mean size -1 or size size 2, 1 or what? Oh, disappeared. We try. Wait. Did it retry the wrong? Did it retry the wrong answer? Broadcasting equals if an axis is size 1. Pretend it's repeated to match. Oh, this answer is very different. Axis and keep dims, the vocabulary. Axis 0, reduce down the rows. Give me one value per column. So per column, one of those values. You have several rows with one value in it. Axis 1, reduce across the columns. One value per row. So you have the columns, what you go like down each row. Keep dims equals true, keeps a size -1 axis. Or keeps a size 1 axis. This has to be like a size 1. Like it means that the size is 1. I might be stupid. I equated a hyphen with the minus symbol. But since there's no space, it probably literally means size 1 as a single word. Keeps a size 1 axis, so shapes line up cleanly for broadcasting. Here it gave you 1, 3, even if you dropped it to 3, 2, 3, 3 minus will also work. We use keep dims to be explicit. Quick send prints to these ones. Print X shape. See column means X shape. You should see 2, 3 for 2 columns. No, 2 rows, 3 columns. And the column averages or means 2.5, 3.5, 4.5. And the shape of the column means is 1 row and 3 columns. And X minus C becomes X still has the same shape, but this time you broadcast this onto each row. Or wait, do you? Yeah, you do. You broadcast this onto each row and remove that much. If the idea still feels abstract, do it by hand once without numpy magic. Compute the 3 means, build a new table by subtracting those from each column. No, this makes sense. That's all NumPy is doing for you, just faster and without actually copying the row. Okay. Then the next one. Wait. This is gonna take a while. B3. Squeeze versus keep dims. Okay, so we define B3. Can't type for the life of me. So still the same thing, so x equals np dot array. I could copy and paste it, but I want to practice writing this. 1, 2, 3, 4, 5, 6. P-type np dot float 64. Still the shape 2 and 3. And then we do we simply print x dot max. Max x is 1. Try not to look at my keyboard at all, but I'm struggling a lot. If that wasn't evident. And max is 1, keep things true. Okay, and then we B3. Oh, so 3, 6. And 1 was the columns. This is the max. We get 3 and 6. Or 3 and 6. And if you keep the dimensions, we have it in 2 rows. But the column 3 and column 6. I think. Am I correct in that? I thought axis 1 was columns and axis 0 rows. Reduce down to rows. Give me 1 value per column. Okay, and reduce across the columns. 1 value per row. So it's still 1 value per row. So it's, yeah, it's 2 rows basically. Okay. So squeeze versus keep dims. So this is the squeeze then. This is squeeze. And this is the keep dims. You'll keep dims equals true inside log some exp, then optionally squeeze on return. Matrix multiply versus element wise. I think we have a good system going here where we go through these and step by step ask the AI for clarifications. I think if we make it through all of these, then we should be able to go back and do the actual exercise. But it's gonna take a while, and I feel like it's not 2 hours, but I did 2 hours yesterday and almost 2 hours today, and I'm feeling my brain melting. There's stuff going on in my life other than my programming as well, so I've been really tired today, and this certainly isn't helping. But I feel like we've made some progress at least. Yeah, definitely some progress. I know more now than I did in the beginning of the stream. Not a whole lot, but I do know more, I'd say. It's a bit clearer, at least. But I'm not sure if I'm going to continue with this tomorrow or if I'm going to do something else tomorrow. I might play some games tomorrow. We'll see how tired I am. Unless I'm feeling like really refreshed, then I'm going to play some games. So yeah, that's all for today. Thank you so much for watching. Have a great evening or morning or whatever. And yeah, cheers.